Prime numbers. For centuries, we've kind of seen them as these chaotic, totally unpredictable rebels of the math world. But what if there's a hidden order, a structure, an elegant and simple one that's just been hiding in plain sight this whole time? Well, today, we're diving into a new theory that says exactly that, a predictable pattern that might just change how we see primes forever.
So on one side, you've got the universe of numbers as we usually picture it, just a big chaotic mess. And on the other, the primes, all lined up and orderly. The big question has always been, how do we get from that chaos to this order? Is there a predictable path? Well, according to this really fascinating new theory, the answer is a big yes. And the secret? It all comes down to a few simple rules.
Our whole investigation really kicks off with the first and, honestly, the most powerful clue. It's called the gatekeeper rule, and believe me, it is the key that unlocks everything else. So where do we even begin with something like this? Well, sometimes the best way to find something is to first figure out all the places it can't be. We start by just eliminating the impossible. And it all starts with these 4 digits, 1, 3, 7, and 9. I want you to think of them as the gatekeepers, because with only 2 little exceptions, any number that hopes to be prime has to end in one of these 4 digits. So this is the gatekeeper rule in action. And when you stop and think about it, it just makes sense, right? Any number that ends in an even digit is obviously divisible by 2. Any number ending in a 0 or a 5, that's divisible by 5. So once you get rid of all of those, the only possible endings left for any prime number bigger than 5 are 1, 3, 7, or 9. Just like that, we've massively narrowed our search. All right, so now that we have our gatekeeper rule, we can actually start building. We're going to put together a blueprint that literally maps out where the primes are. And to do that, we just need 3 things: a set of basic building blocks, a list of all the potential candidates, and a really powerful system to filter out the fakes. Okay, I know, this formula might look a little intense, but trust me, it is way simpler than it appears. This is our blueprint. All it's really saying is that the complete list of prime numbers is made of a few special seeds, plus a big list of candidates, after we subtract all the non-primes that get caught by the filter. So let's break down what each of those things really means. We can wrap our heads around this whole blueprint in just 3 easy steps. First, we'll identify the core building blocks, which we're calling the seeds. Then, we'll generate our big list of potential primes, the candidates. And finally, we'll use the filter to get rid of any imposters. Step 1. The seeds. These are our fundamental building blocks, 1, 3, and 7. Now, I know what you're thinking. 1 isn't a prime, and you're right. But in this system, it acts like a primitive piece for building other numbers. And you probably notice 9 is missing. That's because it's a product. It's just 3 times 3, so it's not a truly primitive seed. Okay, step 2. The candidates. This is where we put our gatekeeper rule to work. The candidates are simply all the numbers, no matter how big or small, that end in one of our gatekeeper digits, 1, 3, 7, or 9. This gives us our starting lineup of potential primes. But here's the catch. Not every number on our candidate list is actually a prime. Our list has imposters hiding in it, numbers like 21, or 27, or 33. We need a way to find them and kick them out. We need a filter. And that brings us to our third and final step. The filter. To find all these imposters, we need a special removal protocol, and this theory has a very, very clever one. So how does this filter actually work? Well, it's created by systematically multiplying our seeds and our candidates together. All the results from those multiplications create what we call the exclusion zone. Basically, it's a definitive list of all the numbers that we know for a fact are not prime. Let's see this thing in action. The first part of our protocol is multiplying a seed by another seed. So for example, take the seed 7 and multiply it by itself. The product is 49. And because 49 is a product of our core components, boom, it gets flagged as an imposter and it's excluded from our list of primes. All right, next up, our second case is multiplying a seed by a candidate. Let's take the seed 3 and multiply it by the candidate 11. The result is 33. And just like that, we found another imposter, so out it goes. And this brings us to the final and really the most powerful case for finding these imposters, multiplying a candidate by another candidate. For instance, 11 times 11 gives us 121. Now that number kind of looks like it could be prime, but our protocol proves it isn't. And what's so brilliant about this method is that it scales up forever, catching all the other non-prime products.
like 13 times 17, which is 221, and so on and so on.
So, after applying our gatekeeper rule and running our product removal protocol, we finally arrive at the end. We have the final blueprint. The mystery is solved.
And here it is, logic restored. After we filter out every single imposter, the only numbers left standing are the true primes. The sieve is complete. What started out as a totally chaotic list has been refined into this perfect, predictable order. It's beautiful.
You know, what we just walked through isn't just some neat party trick. It's a completely systematic way of seeing the number line. Unlike other methods that just cross numbers out, this approach builds everything from the ground up. It shows us not just what the primes are, but precisely why everything else, demonstrably, is not.
It really makes you wonder, doesn't it? If a pattern this clear, this simple, can be found in the prime numbers, a place we all thought was pure chaos, what other profound and beautiful secrets are numbers still hiding from us?